Hi everyone, welcome to the fourth experiment. This experiment is all about implementing a BCD adder and subtractor. That means it should be a single circuit which can work as an adder or subtractor depending on user input. Here, as opposed to previous experiments where we have used logical expressions, this time we will explore directly using Verilog operators of addition and subtraction. From a functionality point of view, what we're looking for is a Verilog module which will take two 4-bit inputs. These 4-bit inputs should be BCD inputs only, that means only between 0 and 9. Rest anything will be considered as invalid. There should also be a selection line, a control line, which will determine which operation should be done. So this convention here means that if the value of the selection line is 0, it will do addition operation, and if it's 1, it should do subtraction operation. The output should be such that we should be able to display the units place of the output on a 7-segment display and display the carry or the sign on an LED. Suppose A is 1001, that's 9, and B is 0111, that is 7. And the control says 0, control value is 0, that means we need to do addition operation. 9 plus 7 is 16. So what we want here to happen is that this 1 should show up in the form of an LED glowing, and this 6 should show up on this 7-segment display as the number 6. Right? We know that we are doing BCD addition, and when we have discussed BCD adder, we have seen that we need to do some sort of correction in the normal binary addition so that the corresponding sum, when it exceeds the value 9, is still on 0 to 9, right? And there is just a carry 1. So please review the notes on BCD adder before going ahead with this experiment. The idea here is that the carry should show up in the LED and the units place should show up on the 7-segment display for addition operation. Let's take another example. Say A is 1000, that is 8, and B is 1, right? And we still say let's do addition. So the control is 0. The output is 9, that is 0, 9. So in this case, the LED should not glow because carry is 0, and 9 should show up on the 7-segment display. Let us take another example where A is 8 and B is 1, and we are doing subtraction. So the difference between the two is 7 plus 7. So since there is no negative sign, this positive sign is sent to the LED. LED does not glow, and this 7 should appear on the 7-segment display. If at all there was a negative subtraction, if the result of the subtraction was negative, like in this case where say A is 1 and B is 8, we know that the subtraction is minus 7. So in case the output is a negative number, we want that negative number to show up on the LED by glowing the LED. So the negative sign shows up on the LED and the number, the absolute value, shows up on the 7-segment display. This is what we want the functionality of our circuit to be. Let us see how the connections should be made. So of course, since we have two 4-bit inputs to consider, we will still use an RPI module just like in the last experiment. We'll give inputs A and B just like in the previous experiment. But this time we also have to give a selection input. Since there are switches available on the pink board, let us use one of these switches for this control selection. So I'm using SW1 in this case. Now to connect outputs, what are the outputs? The 7-segment as well as the LED, right? Just like in the second experiment, we can use P mod B to drive the 7-segment. We could select any of these LEDs to display the carry or the sign. So in this case, I'm choosing LD0. Let us look at how the modules would look like, right? So we have two inputs A and B. And firstly, the whole module should be operational only if the inputs are valid BCD inputs. If they are not valid BCD, means they are greater than 9, nothing should happen. Nothing should be displayed on the 7-segment. So that's the first check you should do, right? Let us also take the control variable. I'm calling it M now. M representing subtraction, minus sign. So when M is equal to 1, we'll say it is choosing BCD subtraction. What should happen in that case? If A was greater than B, you can simply find the difference of A and B, do A minus B, and let the sign bit be set as 0. If A is not greater than or equal to B, then simply reverse the subtraction, do B minus A, and this time set the sign bit to be 1, denoting a negative sign. Note that here we are taking a very short route because this kind of operation is allowed on Verilog. If we were implementing this otherwise, we would have to go through the whole subtractor circuit and use the logical expressions for BCD subtraction, maybe using 10's complement or 9's complement. So we will send this sign bit to the LED, and whatever is this difference, A minus B or B minus A, this should be sent to a BCD to 7-segment decoder, and that is what should go to the 7-segment display. Right? Know that if we were doing BCD subtraction, the minimum value of the subtraction would be minus 9, right? When A is equal to 0 and B is equal to 9. So the minimum value of the subtraction would be minus 9. And the maximum value of the subtraction would be 9, that is 9 minus 0. Okay, so it is clear that since the absolute value will be only between 0 and 9, the BCD input will be a 4-bit input to the 7-segment decoder, right? And it is just the sign that we need to take care of. The other case where M is equal to 0, the user says that a BCD addition should be done instead. In that case, what we will do, we'll just use a simple BCD adder logic where we add A and B, and if their summation is greater than 9, we already know that we have to bring in a correction of 0, 1, 1, 0, so that carry is 1 and the sum part, the 4-bit sum part, just represents the same BCD corresponding digit, right? If this is greater than 9. If you need to review this part, please go through the BCD adder notes again. If A plus B is less than 9, if the binary sum is less than 9, then nothing has to be done. There is no carry output. Simply the sum should be sent out, right? There is no, the carry value is 0. In this case, in case of addition, we will send this carry bit to the LED and we will send this sum to the BCD to 7-segment decoder, whose output will go to the 7-segment display. Okay. At the time of implementation, you should specify A, B and M as the input ports of your module, and LED and SSD combination. The LED bit, which is 1-bit output, and SSD, which is a 7-bit vector, right? These two as the outputs. So make sure that when you write individual modules, you do instantiate this whole thing so that in your eventual main module, the only inputs are A, B and M, and the only outputs are LED and SSD. All the intermediate signals like output values of sum or output values of differences should simply be interconnecting variables. Okay. If this is clear, let us move and see how the Verilog code would look like. So I have created a project, and within that project I have created one design source, which is called BCD underscore adder underscore subtractor. I'm going to write all my modules within this subtractor, and the BCD addition subtraction module, we are defining an input, a 4-bit input A, a 4-bit input B, a 1-bit input M, whose value will determine whether addition has to be done or subtraction has to be done. This is not my main module. I'm going to instantiate it later. For this particular module, the outputs are a 5-bit addition result and the 7-bit 7-segment result. I'm also keeping a C underscore sign. This bit is simply if C is for carry and sign is for the sign in case, depending on which operation has to be done. You may note here that I'm defining out value, this summation, to be a 5-bit vector. This is because when we add binary inputs, it is actually a 5-bit output. Even when we bring in the correction of adding 6, that is 0, 1, 1, 0, the output is a 5-bit number, right? But it is only the sum part, the BCD, the least 4 significant bits that are going to feature into our BCD. The last one is going to be the carry. So just for that purpose, I'm defining it as a 4-bit vector. If we were talking purely in terms of addition, then this carry is nothing but the most significant bit of this out value. But since this one variable is also supposed to be representing sign if we were choosing subtraction operation, that is why I am keeping it as a separate variable. I've defined the module input and output ports. We are defining a temporary output value which will save the value of addition and then check whether it has to be corrected or not. Right? So next we start with a procedural block of always and for all variables within this block, and we begin and first we check whether the inputs are valid or not. That means A is less than equal to 9 and B is less than equal to 9 or not. Right? Only if this is true will this whole loop work. Otherwise, I am defining out value to be some invalid BCD. See, this could have been any invalid BCD. Why I am defining it to be an invalid BCD? Because later what I am defining in the BCD to 7 segment decoder is that if the BCD code is none of these values, like none of the valid BCDs, then none of the 7 segment displays should glow. Means it should not turn on at all. So I am deliberately just giving an invalid BCD value to this variable. Why am I doing this? Is because later in the statement these values are checked, right? So I'm just redirecting it to be to an invalid case if A and B were invalid. If it is not the case, if they are valid BCDs, what are the operations? So we begin another loop and we say if m is equal to 1, that means subtraction. Then begin another loop and check whether A is greater than B. If A is greater than B, then save the value of A minus B to out value. And in this case, the sign is 0, showing a positive value, right? A positive difference. End this loop. Else, if A was not greater than equal to B, then simply do B minus A and save that value in out value and just assign the sign value to be 1. Know that this is just one way of doing this. There are other ways of making a BCD subtractor by using 10's complement or 9's complement. You're welcome to check that out. Then we end this. If this was the case, this whole thing was the case for m equal to 1. Now if m is not equal to 1, that means m is equal to 0, this is the loop for code for addition. Here what we do, in the temporary variable that we had first defined, which was a 5-bit vector, in this temporary variable we save the value of a plus b. We will then check if this value is actually greater than 9. If it is greater than 9, we will say that yes, carry is equal to 1 and output value is nothing but temp, that previous value, plus 6, right? Plus 6. If that is not the case, if the summation was not greater than b, then output value should simply be the temporary summation value. In this case, carry value should be 0. Just to be sure about how the values are being displayed, because on the timing diagram everything gets displayed as a binary value, right? Even if it's a decimal sum. So you may want to display the values of a, b, whether you are doing subtraction or not, depending on the values. These values can be set during the test bench. So this is what does the BCD addition, and this last line was what I already discussed, which is if the inputs were invalid, if A and B were not valid BCDs. Right? So this part of the code, does the addition or subtraction part. Okay. Now the second part of this code, the second procedural statement starting with always, this is nothing but your BCD to 7 segment. Know that out value was a 5-bit register, right? It was a 5-bit vector. The most significant bit is the carry. I am interested in the remaining 4 bits, which is why for my BCD values, I am using a case statement and I am looking only at the rightmost 4 bits and not the full 5 bits. Okay. So depending on the cases of these values, we specify whether one should be displayed. So these are all 7 segment combinations which we've used in earlier experiments. So this is where your this module ends, Okay, BCD addition subtraction. So this will work just fine for simulation. You will get a timing diagram if you write a test bench for A, B and M, and you instantiate this there, and it will work out all fine. What will happen is that when you try to implement this, right, at the time of implementation, when the circuit is being optimized, it will look at what outputs and inputs are there in your code. And you notice that in this particular module, you have A, B and M as the inputs, and you have output values, 7 segment display and the carry, these three as the outputs. However, you do not intend on displaying this output value anywhere, right? That means you will not be assigning this to any port on the pink board or the RPI module, which means that you may face an implementation error at the time of generating bit stream, right? Which is why I am just creating another module, calling it add and sub. In this module, I just take inputs A and B, 1 bit input M, and I take only these two outputs, the carry and the 7 segment combination. I am instantiating this previous module over here, calling this submodule as addition underscore sub, and the output of this module now, this becomes my top level module, right, within the design source. It is this module which will be implemented, and in this module our inputs and outputs, all of these ports, input output ports, will be connected to something in the hardware implementation. Okay, so this is the design source. If we now look at a test bench, so what I've done here is I've created a separate test bench as a simulation source, and this is the code for the test bench. The module name is just test bench. We have defined A, B, M, carry, output value, an intermediate out, which is just going to take those last 4 bits, and the 7 segment output. I'm doing an instantiation of the first module, not the main module in my design source, but because that is okay for test bench, that is going to work just fine. Name of the sub module here is just UUT, another way of saying, say, unit under test. Right? This is the name of the sub module. I'm calling all the ports and connecting them to the signals. I'm also saying that assign to this variable out the last 4 bits, the rightmost 4 bits of the output value. Now, within the test cases, I'm going to specify through the values of this variable m whether we want to do addition or subtraction. So say for instance, we say m equal to 1, meaning subtraction this much. So 9 and 6. In this case, we should see 3 in the output and no carry, right? The sign essentially should be 0. In the second case, we are also doing subtraction. A is equal to 3 and B is equal to 7. Here we should see 4 in the difference, 4 in the BCD, and a minus sign, which means the sign bit should be high, right? LED should glow. Third is another case with subtraction, where I'm intentionally giving an invalid BCD to see what happens, right? One of the inputs is invalid. Another case is for addition. A is 9, B is also 9, so this is the maximum sum that you could have, 18. In this case, 8 should be visible on the BCD and the carry should be high, and so on. Then we finish the simulation. Let us look at how this looks like. So when I run this simulation, this is how the timing diagram looks like. You can see that for the first 3 instances, m was equal to 1, which is why for these first 3, we're looking at subtraction operation, and the remaining 3 are about addition operation. So if we look at the first example, we're doing 9 minus 6. We were expecting a plus 3. So the sign is 0 and the value is 3. In the next case, we were expecting 3 minus 7. We are expecting minus 4. So sign is 1 and magnitude is 4. In the third case, we intentionally put in an invalid BCD, which is why in the code we have put that if there is an invalid BCD, let output value be 15, corresponding to which there is no 7 segment output. So 7 segment will be off completely and no sign should be there. I made a slight change in the code to make sure that when this is the case, C out, the sign should also be 0. The remaining 3 are for addition, and you can cross check how these values are verified. So we can see that the circuit works just fine, and now it's time to make the hardware connection. So I'm going to go to constraints. I've got my RPI and ping port XTCs open. In the RPI, just like in the previous case, I'm going to define these switches for giving the 8 inputs. There is nothing else to do in this RPI XTC file. In the pink board XTC file, there are a few things to do. So one is that we decided that we will use the first switch, that is the SW1 switch on the pink board, to select the operation, right? The control operation. So I'm going to set the port M to this particular switch, which is on the pink board. And we need to connect the Cout or sign port to the LED, one of the LEDs. So we had decided LD0 is what we will select. So this is the first one. Okay. And just like in previous experiments, I'm connecting P mod B to the 7 segment, and this is how I define connection of the 7 segment ports to each of the P mod pins. Now let us look at how the circuit looks like. So now we're going to generate the bit stream and connect the pink port, program the pink port, load this bit stream, and let's see how it works. Okay, so the program has been loaded, and as we decided, we're going to use this first switch for selection of the mode of operation. So right now it's in 0, that means addition is selected. All the inputs are right now 0. Let me select any one of the inputs as 1. So I see 0 plus 1, 0 plus 3, 1 plus 3, I could say 3 plus 2, 5, and this will continue. Let me take something greater than 9. What happens is, say 7 plus 6. 7 plus 6 should give me 13, and at this point you notice that this LED starts glowing. This was not glowing until sum was greater than 9. Like when this was the case, when we were doing 7 plus 0 or 7 plus 1, this LED was off, right? The moment sum becomes greater than 9, say 7 plus 5, carry is equal to 1, and the units place is shown on the BCD. This will continue. Let us also check one of the invalid BCDs. So suppose A is equal to 15, we notice that carry is also off and nothing is shown on the 7 segment. Let us now change the mode of operation to subtraction. So I've moved the switch up. That means now subtraction should be done. Right now still invalid BCD is selected, so let me just make it as 9. So we are doing 1001 minus 101. That means 9 minus 5. So you can see that 4 is visible, and since it's plus 4, LED does not glow, right? Let's check something else which is positive. Say 5 minus 4, that is 1, plus 1, so no carry. Now let us try a negative result, right? That means let's say 5 minus 6. So the result is still, the magnitude of the subtraction is still 1, but since this LED is glowing, it means minus 1, right? I could choose something else, maybe 7 minus, let's say 9, right? 7 minus 9, so minus 2, so 2 is shown and LED is glowing. For any invalid BCD, both the LED and the 7 segment are off, right? Make sure that for both addition and subtraction operations, you take at least 10 combinations to be shown in your video. I hope you enjoyed this experiment. Thank you.